Hi, in this video, we're going to be working in section 10.1. This is the second part 2 of that video. Okay, so we're going to look, we're in the notes here. I shared the notes. And I want to look at the example comparing two population means and independent samples. This is an example that we'll be using as we kind of go through the notes. So it's from the textbook, Driving Distances, Data on Household Vehicle Miles, Data on Household Vehicle Miles of Travel, VMT, are compiled annually by the Federal Highway Administration and are published in these publications. Independent samples of 15 Midwestern households and 14 Southern households provide the following data on last year's VMT, vehicle miles traveled, in thousands of miles. Okay, and so I have the data listed here. I have random samples. Notice that samples, right, the plural there, meaning that there were two different samples. So we do have independent samples here. And also what helps us to see that is that we have different sample sizes. So it will always be the case that if you have dependent samples, that the two groups have the same sample size, the pre and the post. Well, I shouldn't say always, right? What if you lose someone part of the way through the study, someone leaves the study? But for the most part, right, the data you're analyzing. In this case, they have different sample sizes. So we look here, I did some descriptive statistics, and I see that there are 15 Midwest, 14 South, from the South, and the mean is 16.2 for this distribution, Midwest with a standard deviation of 4, and in the South, the mean is 17.7 with a standard deviation of 4.4. Okay, so that's the numerical summary. And let's go ahead and look at the visual summary, the graphical summary. So I prepared two graphs to look at this data so we can just start to get a feel about the two data sets, okay? So on the left is the Midwest, a box plot of the Midwest vehicle miles travel, VMT. And over here on the right is the South. And then so these are our box plots. We see them, you know, I guess we're gonna learn, right? Are these close? Are these consistent with the mean from the Midwest equal to the mean from the South? You know, I have a perspective, but I've seen a lot of pairs of graphs and compared a lot of two distributions. And this is our first time together. But you see here when we look at the histograms that most of the data really is falling in the same area, right? Within the same range. There isn't a big like offset, right? So this, from my intuition, this looks to me like the null hypothesis that the mean for vehicle miles traveled from the Midwest region is equal to the mean vehicle miles traveled from the South region. Okay, so the descriptive statistics tell us that for the samples taken, the sample mean of the Midwest household is 16.2, and for the Southern, 17.7. We see that's what I just reviewed, and these are just samples, right? We do see that there's a difference in the X bars, but they're samples, and what we're interested in determining in the study is whether we have evidence to show that the population means differ. And so basically the question boils down to is the difference between these values, 16.2 and 17.7, is it small enough to be explained by the inherent variability in the system? Or does it really indicate a difference in population means? And how do you figure that out? Well, you look at the differences and you will look at the variability. And we're going to do that by forming a test statistic. Okay, so let's go ahead and set up the probability structure here. We're going to build notation, and I'm going to go over some distributional results. So for the first distribution, we'll use population mean mu1 and population mean. For the mean of the first distribution, we're going to put a little 1 here, a subscript 1. So mu1 comes from population 1, sigma 1 from population 1. So we're just going to add to our standard notation the subscript 1, and that will indicate that it comes from the first population, however we define that. And then over here, we're going to do the same thing for all the population 2 values. We're just going to, whether they're population values here with a 2 or whether they're sample values, they also get the subscript 2. So that's our notation that we're going to be using in the chapter. And then normal results, normal distribution results. Suppose that X is normally distributed variable on each of the two, that X is normally distributed, that the VMT, for example, VMT from the Midwest, from the Southern household is normally distributed, and the VMT from the Midwestern household is normally distributed. So suppose that X is normally distributed, and then for independent samples of size N1 and N2 from the two populations, we know that the mean, well, we want to compare mu1 and mu2, right? So we look at the difference of mu1 and mu2 and see if it's equal to 0 or not equal to 0. Okay, and that's going to be the direction that we use in terms of how we compare. So we're interested in then the distribution of x1 minus x1 minus x2, and we see that mu of x1 minus x2 is has a mean. The mean of the distribution of x1 minus x2 is mu1 minus mu2. The standard deviation of the distribution of x1 minus x2 is has this form here, the square root, and then it's the sum in there of sigma 1 squared over n1 and sigma 2 squared over n2. I'll show you how to use these formulas. They seem a little weird, but we'll get comfortable with them. This is an area where my students do get a lot of success, so we'll just kind of go through the problems, and even though it feels like a lot of notation right now, we get kind of used to it. And we're also making this assumption that the mean of x1 minus the mean of x2 is normally distributed. Sample means. And so because we have all of that, we can look at this z statistic here. Notice in the numerator, I have x1 minus x2, x bar 1 minus x bar 2, excuse me, minus mu1 minus mu2, okay? And in the denominator, I have that standard deviation, which we spoke about, okay? So we're going to be working in one of 3 situations for the null and alternative hypotheses. And I just want to set this up both. I'm just going to set up in this section what the null and alternatives would look like. I want to discuss what a confidence interval looks like and what it means. So just get that kind of perspective on how we're going to use the data. So if I'm interested to know whether mu1 is equal to mu2, we're going to rewrite that. We could also rewrite this as the null hypothesis is that mu1 equals mu2. We can say it's mu1 minus mu2 equals 0. And we can also, and so either of the null hypothesis mu1 equals mu2 or mu1 minus mu2 equals 0, they are equivalent. Alternative hypotheses are either going to have a not equal sign, a less than sign, or a greater than sign, depending on if you're just interested in flagging a difference or if you are interested in determining if mu1 is less than mu2 or mu1 is greater than mu2. And again, we're going to look at the problem and find keywords in the problem to help us figure out which of these 3 alternative hypotheses are what we need to solve a problem. So we can compare 2 means using a hypothesis test, but we can also find a confidence interval for the value mu1 minus mu2, okay? So, and so there are 3 different situations that I want to look at for the confidence intervals, okay? So either the confidence interval, both ends of the confidence interval. So okay, so I guess I jumped ahead a bit. I want to talk about how what the confidence interval, how it's interpreted, all right? In the next section, we'll talk about how to calculate it. So there are 3 important situations, right? So I'm going to highlight them here, where the confidence interval includes both numbers being positive, or the second one, both numbers being negative, or the third situation where you have the lower one is negative and the upper one is positive. Okay, so if my confidence interval for mu1 minus mu2 has both ends positive, then that's consistent with the statement, we are 95% confident for this example, right? That 5 is less than mu1 minus mu2 is less than 8. So we are 95% confident that mu2, adding mu2 to all three parts of this expression, mu2 plus 5 is less than mu1, is less than mu2 plus 8. So we are 95% confident that mu1 is between 5 and 8 units more than mu2. Okay. And over here, if we have a situation where both endpoints are negative, then we are, for example, we are 95% confident that mu1 minus mu2 is in the interval -4 to -1. Then we could be 95% confident that -4 is less than mu1 minus mu2 is less than -1. And we can add mu2 to all 3 parts of that expression, and we get that we are 95% confident that mu2 minus 4 is less than mu1 is less than mu2 minus 1. And so we are 95% confident that mu1 is between 1 and 4 units less than, so we think that mu1 is less than mu2. Up here, we were able to determine that mu1 is likely greater than mu2, okay? And here when we have 1 point in the negative and 1 point in the positive, then we are 95% confident, right, that -3 in this case is less than mu1 minus mu2 is less than 2. We can add mu2 to all 3 parts of that expression. And so we have that mu2 minus, we are 95% confident that mu2 minus 4 is less than mu1, is less than mu2 plus 2, all right? And so we are 95% confident that mu1 lies between 3 less than and 2 more than mu2. So in particular, it's possible that mu1 minus mu2 equals 0. So this is a situation that's consistent with our null hypothesis, right? That mu1 minus mu2 equals 0. So if we get a confidence interval and we find that 0 is in the interval, it means that it's reasonably likely that mu1 and mu2 are equal, okay? And then the other situations tell us whether we think mu1 is greater than mu2 or we think mu1 is less than mu2. Okay, so that's it for section 10.1. There's just a lot of ideas and definitions. We're not going to be doing too many problems in 10.1, but it sets us up to do some work and to compare means from 2 independent distributions. We'll be working with that procedure, hypothesis testing procedure, and confidence intervals in section 10.2. I'll see you in the next video.